All right, here we go. Another lecture. This one on 3.8, the derivative of inverse trigonometric functions. Also, probably we're going to spend just some time just talking about inverse functions in general. Functions have inverses, important function pairs that are inverses of each other, x squared and the square root of x are inverses of each other, meaning that if I take the square root of x squared, or if I take the square root and square it, both times the two functions cancel each other out. They're inverses of each other. Couple of interesting about inverse functions. Functions have to be monotonic, meaning they only can be increasing or decreasing, not both. And a quick reminder that a function and its inverse have this relationship that if f of a is on one curve, then f of a is on the other curve. I kind of like to summarize this, going off screen here. I like to summarize it thinking about sort of a most famous pair of inverse functions, and that is the function f of x is equal to e to the x, and we can have g of x is equal to the natural log of x, and these two are inverse functions. The natural log of e to the x is equal to e to the natural log of x, and they both cancel each other out and leave one. For every point that's here, call it AB, there's a corresponding point on the other side, BA, right? And it so happens that those two corresponding points are always the reflection of one point across the line y equals x. So every time I think about inverse functions, I tend to just draw these two curves. Now, one of the other things about inverse functions that are very interesting, that is, if you take this slope of the tangent line at AB, let's call it slope m. If you go to the corresponding point, it's going to be 1 over m. It's always the reciprocal. No changes of sign, nothing like what would make it a normal or a perpendicular, just the reciprocal of it. All right, let's see that idea in action for this particular example. Compare the graphs and the slopes of y equal x squared with y equals square root of x. Okay, so y is equal to x squared. So dy dx is equal to 2x. Y is equal to square root of x, which I'm going to write as x to the 1/2. So dy dx is, let's bring the power down, and then let's reduce the power by 1, which is equal to 1 over the square root of 2. Now, at first blush, these don't look like reciprocals of each other, but let's just try this out. Okay, I'm going to choose a point on the curve y equal x. Sorry, y over x, is it yx squared? How about 2 comma 4? Right? So the derivative at x equals 2 is 2 times 2, which is 4. Now, this is my graph of y equals the square root of x. What is the corresponding point on the inverse function curve? Well, that would be the point 4 comma 2. So let me go over here. Dy dx at x equals 4 is equal to 1 over the square root of 4, which is 1 over 2 times 2, which is 1/4. Oh, one has a slope of 4, the other has a slope of 1/4, and we could do that all day. All right, so big idea. And again, my tendency, whenever I get a inverse function problem, I draw the e to the x curve and the natural log curve, and I think about the corresponding points that have their coordinates reversed. Now, believe it or not, we can apply this idea, or the idea of implicit differentiation, to actually find out that inverse trigonometric functions also have derivatives. And I think it's a very surprising derivative. Inverse sine of u where u is some function of x. 1 over 1 minus u squared times du dx. By the way, just a note, what's this thing called? Oh, it's the chain rule. Remember, u is some function, so inverse sine of u is like inverse sine outside function, u is the inside function. Before we apply this, let's prove it. I mean, it says here, we can look at the video of the proof. The proof isn't that hard. In fact, I think I could do the whole proof right here. Let's say y is equal to, and I'm just going to go with the inverse sine of x. Right? If that's true, I could take the sine of both sides of the equation, and the nature of a function and its inverse is that they cancel each other out. So now I've got the sine of y is equal to x. Let's take the derivative of that with respect to x. Oops. Over here, the derivative of x with respect to x of x. This is going to end up being 1. Over on this side, we're going to get cosine of y dy dx. Well, that's fine, because what I'm interested in is solving for dy dx, 1 over cosine of y, and that doesn't look anything like that, does it? But let's go back to this idea, which I'm going to highlight right here, that the sine of y is equal to x. That means I'm thinking about a right triangle, and sine of something, y must be an angle, and x, or x over 1, must be the ratio of the opposite side to the hypotenuse. So I've got a right triangle with a angle y, an opposite side x, a hypotenuse of 1, and if you do a little bit of Pythagorean theorem, you can find out that this ends up being 1 minus x squared. Now, I ask the question, what is the cosine of y? The cosine of y is the adjacent divided by the hypotenuse. And I could write over 1, but I don't have to, because it's just dividing by 1. Hey, the derivative is 1 over square root 1 minus x squared. And if we write it generally, then it's u. Okay, let's apply that. Hey, what's dy dx? 1 over the square root of u squared, or 1 over 1 minus u squared. U squared, or sorry, u is that. So how about 8x squared squared? Great. And because there's an inside function here, I need a chain rule, and that chain is going to be 16x. So I might finish this off by saying the answer is 16x over the square root of 1 minus 64 x to the 4th. And I would leave that answer just like that. All right. Now, likewise, we could show that this is the derivative of tangent, or sorry, inverse tangent. Same idea, same proof. In fact, I'll leave it to you to find out that it is indeed 1 over 1 plus u squared. I forgot to do this on the earlier slide. Stars, you know what that means. You're gonna have to memorize that. Stars. Okay. All right. So let's go ahead, and if we believe that's true, we should be able to say, what is the derivative of the inverse tangent of square root? I'm moving the so let's see. X is a function of t. So if I take the derivative I get the screen right. I'm going to take the derivative with respect to t of x of t. I'm going to take the derivative with respect to t of inverse tangent of the square root of t. All right, x prime of t. derivative of a position with respect to time. We have another name for that. We'll call it velocity. And inverse tangent, 1 over u squared. 1 over 1 plus u squared. 1 plus, and u in this case is the square root of t squared. And then we have a chain rule, which is the derivative of the square root of t. Remember, the square root of t is t to the 1/2. The derivative of t to the 1/2, bring down the power, reduce the power by 1. That ends up being 1 over 2 root t. Or to clean this up, we get 1 over 1 plus t times 2 root t. All right, great, but we haven't answered the question. The question is, what is the velocity at t equals 16? Velocity at 16 is going to be 1 over 1 plus 16 times 2 times the square root of 16. 1 over 17 times 2 times 4. Oh, it's so difficult to do math at this time of night. 17 times 8, 56, carry the 5, 13, 136. How about 1 over 136? I really hope that's right. Again, knowing this is true, you can prove it yourself, or you can ask me, and I'll gladly sit down with you and we can work it out together. Okay. Lastly, the derivative of arcsecant or inverse secant. It's got extra little fiddly bits, absolute values of u, and then square root u squared minus 1. If we do this particular formulaic, and again, oh, I forgot to put the stars. Okay, and memorize that one. It will be 1 over absolute 3x minus 4 times the square root of 3x minus 4 squared minus 1. And then multiply it by that chain rule. What's the chain here? The derivative of the inside? It's 3. So how about 3 over square root 3x minus 4 over, and again, I'm not going to expand that. There we go. There's our answer. Okay, so we've done 3 inverse trig functions, the sine, the tangent, and the secant. You got to memorize those 3. The good news is the other 3 are easy to memorize. Take a look at the difference between inverse sine and inverse cosine. What's the difference? Answer, the difference is only that negative sign. I don't know why my pen's not working. And cotangent and tangent, again, only that negative sign. And inverse secant and inverse cosecant, only that negative sign. So if it's got a co, the derivative's got a negative sign, and otherwise everything else is exactly the same. All right, let's do one more. What is the derivative of the inverse cotangent of x squared? All right, and we've got our guide, cotangent, so it's got to be a -1 on top. Tangent was 1 plus u squared, and in this case, u squared is x. U is x. U is x. So we get -1 over 1 plus x squared, and then we got a chain rule, which is 2x. Cleaning it all up, how about -2x over 1 plus x to the 4th? And that's it. We're done.